And if we could have our next speaker up to the podium. Our next speaker is Chao-Chi Chen, who is I hope I said that right, who is studying for a PhD at UC Davis and is intern at Microsoft. Just so that you know you don't have to fit into 15 minutes, you do actually have the full 30 minutes. We're going to go to the coffee break at 4:15. And then the BOFs are going to start at 4:45. So we're just going to shift everything back about 15 minutes so that so we've got time to hear the full talk.
Thanks. Thank you. Hi, again, my name is Chao-Chi Chen, and today I'll be presenting BGP Sharp, a system for dynamic route control in data centers. This is a collaboration project between Microsoft Bing and Microsoft Research. So to begin, let's briefly look at the makeup of the data center environment. In data center, there's what's called the tenant and landlord system, where there's one landlord who's the owner and manager of the data center, and you have many tenants who are the user of the data center resources. The tenants can be classified into two different categories. One is called internal users, where it could be user from your own search division, mail, online gaming, etc. And the second class is what's called the external users, and that could be the customer of your utility computing. And there are many challenges in data center. Today, I'll only be focused on empowering tenants with the ability to control routes. So the routing intention inside the data center is as follows. The tenants, they have many different goals, but for a lot of their goals, they ultimately want to be able to control the routes dynamically and on demand. But at the same time, the landlord who manages the shared infrastructure, they want to make sure that they can empower the user, but also at the same time control any bad behavior that the tenant might have and ensure the system is scalable. So an example of a tenant goal is to spread traffic. So here you have incoming traffic going to router, and your goal is to spread the traffic between two servers at the 192.168.0.2 and .3. And a second goal is to migrate traffic. So instead of spreading it, you want to move the traffic from one server to another. So currently, the way you would perform these changes is as follows. First, the tenant would submit a ticket to something called a ticket distribution system, and the system would assign a dedicated admin to the ticket. Then, the admin would clarify the requirement in the ticket with the tenant, which would require several rounds of communication back and forth. Once the requirement is clarified, the admin creates a route configuration for the ticket. And again, the admin will show the tenant the routing policy to make sure that the routing policy satisfies the requirement in the ticket, which will also likely be several rounds of discussion as well. And once the routing policy is confirmed with the tenants, the admin will confirm that with the tenant, and it will resolve the ticket in the ticket distribution system. And finally, the tenant is notified that the ticket is resolved, and the above process is simplified. And there are three major problems in this sort of framework. First, tenants, they have very little control of routing. The only thing they can do is to specify requirements that they want in a ticket. And in a system where the ticket might propagate over several ticket distribution systems, the requirement might have lost its translation along the way. And the second problem is that there's a dedicated human resource required for each ticket. And lastly, there's a lot of manual configuration on the part of the network admin. And as such, the ticket resolution time might be very long. So based on these problems, it would be nice to have a good system to deal with this. And the system should have the following properties. First, it should allow for some sort of automated route control through the use of application programming interface. And second, it should allow tenants independent and safe route control, and at the same time validate any requests that the tenants might have. And third, it should ensure better scalability at two levels. The first level is system scalability by factoring out policy control. And the second level is human resource by eliminating the need for a dedicated admin per ticket. And lastly, it should tolerate failures and plain maintenance through deployment of redundant components. So the solution that we suggested is called BGP Sharp, and it contains three components. The first component is a simple speaker, which I'll refer to as multi-speaker from now on. It pairs with BGP routers, and it just sends route announcement in withdrawals. And when a single multi-speaker instance is able to set up multiple peering sessions with the router, so it's able to perform ECMP. And the second component is a stateful controller that from now on I'll refer to as controller. It controls and coordinates the speakers and exposes public API to the tenants. And the last part is the tenant client application, which I'll refer to as application from now on. It discovers the services offered by the controller's API and modify routing to the tenant's network via the control API. And the BGP architecture looks something as follows. On the lower right-hand corner, you have the tenant's logical network connected to the router as usual. On the left, you have multiple multi-speakers connected to the router, and each of the speakers is also connected to the controller. And the controller finally have an exposed API to each of the tenant's application. So let's look at how we can use this architecture to solve the tenant goals that I previously mentioned. For the first example, I want to look at migrating traffic. So what I'll do here is that the application from the tenant will issue a route change request, something like move the next hop from one server to another. And then the controller will actually validate and forward that request. When it gets to the speaker transforms that request into BGP messages and send it to the router. So the router will update its routing table. So in this case, it will move the traffic from 102.168.0.3 to 182.168.0.2. But there's a caveat. The multi-speaker needs to have announced the original route in order for this migration to succeed. And the second example is to spread traffic. And here, the setup is as follows. In the multi-speaker, I have two BGP sessions to the router. And the first session of the multi-speaker have already announced an existing route, and the router has enabled ECMP. So what I'll do here is something very similar. The tenant application will send a request to say, I want to spread the traffic to another server. Can you please do that? And the controller will validate and forward that request to the multi-speaker. And the multi-speaker will use the second peering session to send that request into a BGP message and send it to the router. So in the next couple slides, I'm going to briefly talk about the properties of BGP Sharp. The first is automated route control. So automated route control is basically the controller's API allowing tenants to develop their custom application. And those applications can automatically manage routes to meet the tenant's goals. At the same time, those requests are being validated. And in the table below, I have two examples of route control program that can satisfy a certain goal. So for example, if you would want fast server failover, you can have a program that replaces dead server IPs with live server IP. And in the second example, if you want high throughput, you do something similar where you replace IP of servers having heavy link utilization with IP of servers having light link utilization. The second property is independent and safe route control. To achieve independent route control, we allow tenants to control their routes independently of other tenants. So each tenant can install their application into their own network in their own box. So the effect of one tenant is isolated. And to achieve safe route control, what we do is we have the controller enforce routing policies via a database. And the database will look something like the red box on the left, where you have a list of tenants. And for each tenant, there is a valid address space for which the tenants can manipulate their routes. So for example, if tenant wants to manipulate a route in the address space of 10.10.26/24, the controller wouldn't honor that because the tenant is not allowed to do so. Tenant A is not allowed to do so. And in terms of scalability, as I mentioned previously, we want to achieve scalability at the system level and human resource level. At the system level, we achieve BGP Sharp achieves scalability by factoring out policy control, meaning that the multi-speaker and the controller are not placed in machines that are handling user traffic. And by doing so, BGP Sharp eliminates the need for having one policy controller per machine. And it also reduces the number of peering sessions needed to the router, because now we don't need to have every machine that needed custom routing to have a BGP session to the router. And to make the human resources scalable, BGP Sharp eliminates the need for dedicated admin per ticket by ensuring that the policy is enforced at the controller. So there's only a few admins needed to configure the policy at the controller for all the tenants. And this also guarantees that any tenant routing behavior are isolated from others. The next point is resiliency. And The BGP shard system strives to achieve two types of resiliency. One, the first is called system resiliency, and this is to ensure that the system continues operating even when any single component in the system might fail. And BGP shard achieve that through two means. First is to instantiate multiple multi-speakers, so that a single multi-speaker failure does not affect other multi-speakers' availability. And the second point is to separate the multi-speaker and the controller. So when controller fails, the multi-speaker is not affected. And to ensure prefix resiliency, meaning we want to make sure that the prefix stays available even when components might fail, there's also two methods. The first method is announce the same prefix from multiple multi-speakers. So when a single multi-speaker fails, the prefix will still be available in the router from the other multi-speakers. And second is also to separate the multi-speaker and the controller. So when the controller fails, the prefix is not affected. In the following couple of slides, I'm going to give an example for prefix resiliency. And the setup is as follows. I have a router at the top and two multi-speakers, speaker A and B, that have a peering session established with the router, and I have a controller. So first, both multi-speakers announce the same /32 prefixes VIP1 and VIP2 to the router, and the router installs it in the routing table. And now suppose multi-speaker B fails, the VIP1 and VIP2 from multi-speaker B is removed, but the VIP1 and VIP2 from multi-speaker A is still there since the session is still there. So the end result is that VIP1 and VIP2 is still available. And we can have some kind of automation service that's an overarching manager of the data center to instantiate a new instance of multi-speaker, let's call it multi-speaker C, and have the controller pull a configuration from a persistent store to restore the prefix redundancies. And next, let's suppose that the controller fails. In this case, multi-speaker A and C, their peering session with the router is still there. So both VIP1 and 2 from both speakers are still there. So the prefix availability is not affected. And also, we can have the automation service instantiate a new instance of the controller. So with this multi-speaker setup, we thought about, well, is there any problem with inconsistency? So let's consider the first scenario where some multi-speaker become unresponsive, and when the controller sends force a request to add or withdraw certain routes, how do we know it's actually withdrawn or installed into the router? The way we overcome that problem is to have a BGP listening to that listens for router readvertisement. So if we receive a router readvertisement for withdrawal and for announcement, then we know that the router has removed or installed the routes. And in the second case, suppose the multi-speaker reboots and is in a different state than other multi-speakers. In that case, the multi-speaker will obtain the configuration from a persistent store, as shown previously in the prefix resiliency example. And of course, there might be other alternate approaches. For one, each tenant can set up its own BGP instance to control their own routing. In this example, the tenants need to depend on the ticket system, because now when they set a parent session, they need to go through the system admin every time they add a new BGP instance, and the BGP instance operation might be delayed because the problems mentioned previously. And on the other hand, the landlord needs to deal with potentially many BGP peers, and this requires a lot of manual configuration, dedicated human resource, and as the number of BGP peer instances increases, the maintenance complexity also goes up. So in conclusion, the BGP architecture allows the tenant to have more power to control their own routes by the use of the application programming interface. But at the same time, the landlord still retains the responsibility of validation and whether the announced routes can propagate to upstream routers. And lastly, the system achieves scalability and resiliency through distributed component and redundant components. And this is my presentation. I have a live demo, but it's difficult to show on the screen. So if you're interested in looking at demo, please find me after the talk. And now open for questions.
Yeah, I couldn't help but thinking that, is this on?
Yeah.
Yeah, I'm Paul Francis. that BGP seems like a pretty coarse-grained tool to be doing something like this. Why not, something like MPLS with traffic engineering or something to really set up the flows?
So the reason that the main reason that motivated us to use BGP in the first place was when we look at several different routing protocols like OSPF, ISIS, and BGP, we realized the BGP finite state machine is fairly simple in itself. There's only several states, and the message that we need to construct are very small. The biggest part that we need to configure is the update messages, and also at the same time, the BGP allows us to have policy filtering on the router, and just considering all those, we picked BGP, but we didn't look too much into MPLS. Yeah, so that's a good point. I will. Any questions? All right, thank you very much.
Okay, if there are no more questions, thank you.